we're going to do that one, but this is actually problem number 4. It says a cone has a diameter. So here's my cone, and that means the radius is 5, right? And a height of 15. So the ratio of radius to height will be 10 to 15, or just we'll just leave it at that. It says water is being poured into the cones at the height of the water level is changing at a rate of 1.2 inches per second. And that height, dH dt, I'm going to write it right here. dH dt is positive because it's increasing. Okay? It says at the instant when the radius of the exposed surface area of the water is 2 inches, at what rate is the volume of the water changes? So the exposed surface area, so the surface area is going to be the area of that circle. So the area of the circle, and I just like to do that so I'm sure about what I'm talking about, and that's just pi r squared, and it's 2 inches. 2 inches. It should be squared. At what rate is the volume of the water changing? So, a lot of variables involved. I have heights. I have a height of 15. I have a cone with a radius of 5 at its peak. And what else do I have? The radius. Oh, so this is when the radius is 2 inches. Okay, so the radius is 2 inches. So if I needed to find the height for whatever reason, I could, because I know the ratio of the radius to the height is 10 to 15. That means if I set up a ratio of the radius to the height, I have 10 over 15, and it says when this is 2, the height should be whatever this is. So if I cross multiply, that height is 3. The height is 3 at this point. At this very instance, the height is 3. And I can solve for it. There's multiple ways to go about doing this, but this one works. All right. So it says dH dt is plus 1.2 inches per second. What is dV dt? So let's look at this equation. So the volume of a cone is 1/3 pi r squared h. So I have two things going on here. So I'm going to have to, when I implicitly differentiate, when I go to work to get dV dt, I'm going to have to write this in terms of the product rule. Okay, so let's figure out what f of x is. So f of x, this is a product, right? So I can say f of x is pi r squared over 3 or 1/3 pi r squared, however you want to write it. I'm just going to do both of them because people are used to seeing, like they're not always used to seeing this in this way. So I wrote both of them just for that, for the sake of that. And I get 2/3 pi r squared, or, and this is dr dt, or you could write 2 pi, it just doesn't make sense to write it this way because you require parentheses, but it's easier to write it this way, or you could even write 2 pi r squared over 3, and this would include your dr dt. Anyways, so g of x equals h, and g prime of x is dh dt. So just filling this in, f prime of x, I'm going to write 2 pi r squared over 3 dr dt, and don't forget you're multiplying h, plus see dh dt, and we're going to rewrite this appropriately, times my f of x, which is 1/3 pi r squared. So I'm going to rewrite this appropriately, and I have dv dt equals 2 pi r, oh, I gotta get rid of that squared right there, 2 pi r, make sure that's squared because that should have came down, 2 pi r, right, h times h over 3 dr dt plus pi r squared over 3 dh dt. So all of this goes to the front. And I'm going to plug stuff in. So I have a radius and I have a height. I have a rate of change. Radius and height, 2 inches and 3 inches. dr dt. Oh, dh dt is 1.2 seconds. 1.2 inches per second. And here's the conundrum, and this is why I did this separately, because people ask me, why would you put this in terms of only one, one variable? So this is the conundrum I have here. So if I plug this in, 2 pi, I have 2 times 3 over 3. I have no dr dt. I have pi, I have 2 squared over 3 times 1.2, that should be dh dt. Okay, so unfortunately, I do have to go back through and make some changes. So I'm going to do this on the other side. Okay, and we're going to start right about here-ish. Because I have a problem. I can't solve for this changing volume because I don't have a rate for the radius over time. If you want to go back and follow through that, you'll see what I mean. And this is also why I made these separately, for this very reason. I didn't want to spend a billion hours trying to explain one problem to you. Okay? So here's where we're at. I have to do this particular problem in terms of the height. So I'm going to solve for the height in this problem. All right. And the way I do that is I take that same ratio, and I'm going to solve for the radius actually. I take that same ratio. All right. Apparently I can't do anything with that. Take that same ratio I had earlier. The fact that the radius to the height is 10 over 15. I need to replace all the r's in that volume equation. Here's the volume equation for this cone. It's pi r squared h over 3. I'm going to replace this r. So this r equals 10 over 15 times h, or that's 2 over 5. No, yeah, no, 5, 2 over 3 h, or you could write 2h over 3. All right, so here this becomes pi 2 over 3 h, and that's all squared over 3. This equals pi 4h, and that's cubed, and that 3 becomes 9, and it's going to drop down and become 27. Okay, now I can get dv dt. Okay, and this is going to work for me. So I get the derivative over here. I have 12 pi h squared over 27 dh dt, and I have everything I need. I have the height, which is 12 pi 27. The height is 3 at 2 inches. It's 3. I figured it out earlier that dh dt, this depth right here, is 1.2. Okay, and I get, let's see, 12 times 9. I get 4 pi times 1.2, and I get 8.4 pi. I'm going to go get my units here, and I have inches cubed per second. All right, and that's all she wrote, and I will be doing these ladder problems. These are pretty important. It goes through the 3 types of triangles you might be approached by. I'm going to save this and end it right here.